champions, welcome back to the Brahmastra 2.0 series, and in today's video we are going to discuss the most important questions from the chapter alcohols, phenols and ethers. So in this video you will be getting questions from name reactions, mechanisms, all types of questions that is possible. So if you watch this one video and practice these questions, then you will be able to get full marks from this chapter in your final board exams. So let me first explain you the weightage of this chapter. So alcohols, phenols and ethers carries 10 marks in your final exams. Now how is this 10 marks distributed? So you will be having one 5-marker question, one 2-marker question. So 7 marks are done here and 3 MCQ questions you will get. Not MCQ, 3 1-marker question. This 1-marker can be in the form of MCQ plus fill in the blanks. Okay, so overall 10 marks will be there from this chapter. So very important and high weightage chapter. So let's start with some very easy, that's not easy, but yes, very tricky MCQs, and these all MCQs, let me just tell you, these all MCQs are HOTS questions. Okay, so let's start with the first question here. Propene is allowed to react with HBr in the presence of benzoyl peroxide and the product is subsequently heated with aqueous KOH. The final product is. Now this is a simple question. Now if you see propene is there, okay, and if you are reacting with HBr in presence of peroxide, okay, HBr and peroxide, so what will happen? Bromine will be added to the last carbon, okay, because it is peroxide effect, anti-Markovnikov rule is followed here, right? So I will have C, so we will have something like this. We will have like this, okay. Now when you treat it with aqueous KOH, okay, when you treat it with aqueous KOH, what will happen? This Br will be replaced with OH group. Okay, so this will be the product propane 1OL. So that is your option number C here. Okay, next we'll see the question, the ether C6H5O CH2 C6H5 on treating with concentrated HI produces. This is a very important concept. Now I want to take some time and explain this concept in detail. Okay, now there's a topic called cleavage of ether. So what I'm teaching here now, please note it down because this is important. Now when you have this ROR dash, okay, and when you treat it with HI, okay, so what happens? This oxygen first takes this H plus, okay, and it gets protonated to form a compound like this. Okay, now after that what happens? I minus will attack. Okay, I minus, if it attacks on this one, this bond will break and you will get ROH plus R dash I. Right, this will be the reaction. Now here something important you have to understand is, where will this I minus attack? Why it will attack on this side, or in which case it will attack on this side? So there is something that we have to understand. Now if both the R groups, now see, if both R groups, okay, if both the R groups that we have are primary or secondary, okay, then the reaction proceeds by SN2 mechanism. Okay, reaction proceeds by SN2 mechanism. Now if the reaction proceeds by SN2 mechanism, then this nucleophile will attack on the less hindered site. Will attack on less hindered site. Okay, will attack on less hindered site. What do you mean by less hindered site? Where there are less number of carbons. Okay, and if the same number of carbons is there, then where there is less branching, okay, that is less hindered. Second point here is, if out of this any one group is tertiary, out of this R group, one side is tertiary, then reaction proceeds through SN1 mechanism and I minus will attack on, or I minus not, nucleophile will attack on what? Will attack on the tertiary group. Okay, so R will attack on the tertiary group. Whichever side is tertiary, there I will be attached. Next thing, if any of the R group is having benzene, or I'll say if in this ROR, if R is benzene, okay, if ROR, then R is benzene, okay, if R is equal to benzene, then I, okay, or sorry, then nucleophile, I'll write like this. If R is equal to benzene, then nucleophile will always attack on, always, remember here I am using the word always, okay, will always attack on R dash, okay. So if one side is phenol, then I will, or the nucleophile will always attack on the other side. This bond cannot break, okay. You know, we have studied that there will be resonance. This bond is a partial double bond character, very strong bond. So nucleophile will always attack on this one, okay. Next, if you have any phenyl or benzyl, you can I can write not phenyl, sorry, allylic. If you have allylic or benzylic carbocation, okay, if we have allylic or benzylic carbocation, in that case nucleophile will attack on it, okay. If there is allylic or benzylic carbocation, then nucleophile will attack on this one. Now I'll give you example for all these 4 steps so that it will be clear, okay. So now let us take the example 1 here, okay, for the first one. This is 1, 2, 3, 4 cases, 4 cases are there. So for example, if I have CH3O, CH2, CH3 and I'm treating with HI, okay. Now first there will be protonation here, after that nucleophile. So you can see here this is primary, this is also primary. So the reaction will occur by SN2 mechanism and the nucleophile I minus will attack on the less hindered side, right. So first O plus H will be there, then I minus will attack here and this one will form the ROH, right. So what will be the product here? Here the product will be CH3I plus CH3 CH2OH. Clear, the first one. Next, the second thing is tertiary. If you have one group is tertiary, example 2, okay. If I have CH3, CH3, CH3 and we have OCH3, okay. Then if I react this one with HI, then again here there will be protonation, and here I have told you if one side is tertiary, then I minus will always attack on the tertiary group. So I will erase this part, okay, so that I can explain you all the examples and I will need some more space here, okay. So now understand, if this one side is tertiary, one side is primary, then reaction goes by SN1 mechanism. I will attack here and I will get CH3 whole 3 Ci plus CH3OH, okay, clear. Next, coming to example 3 we have, okay, what is example 3 here? If you have one side phenol group, so if you have a compound like this, phenol, then I have CH3. In that case, I will always attack, if R is this one, then I will always attack on R dash. So if this is R dash, then I will always attack on this one and you will always get a product phenol plus CH3. Okay, now we'll talk about the fourth example, which is very, very important. That is, if you have a compound like this, CH2O, CH2, CH3. Okay, now here you see this is also primary, this is also primary. Now you may think that if both are primary, then nucleophile will, the SN2 mechanism will follow and nucleophile will attack on the less hindered side. And if you see this is having a bigger molecule, this is having a lesser molecule, so this is less hindered side, so I minus should attack on this one. No, but here you have to be very careful that the carbocation that is formed here, means first there will be O plus H protonation, right? After that, if this bond breaks, there is a carbocation formed here, and this carbocation is highly stabilized due to resonance, Now if that is happening, if there is stabilization due to resonance, then the nucleophile will attack here, okay. So what will happen in HI? So I will get this one, okay. This one is CH2 I, and then we have CH3 CH2OH. Clear? So these are the 4 examples. This is 1, 2, 3 and example 4. I hope the 4th example is clear when I'm saying that if you have a benzyl or an allylic carbocation, okay, in that case nucleophile will always attack on this side and the other part will form the alcohol. Okay, now if these 4 examples are clear, we can go and solve our question. Okay, now please take a screenshot here or note down, because when I save the PDF, this slide will not be there, because this is not the slide, it is just like to explain. I have take this, so it will not be saved. So please take a proper screenshot or pause the video and note down this one. Okay, so I am now going back to our question. Now the question here that we have is C6H5, okay, C6H5O, CH2C6H5. This is very easy question after we have understood here. Now see, if there is phenol group of, if this group is there, then I have told you blindly you have to attach H here and I here. So what will be my product? Here you will have, this one will give you OH, okay, and this one will give you CH2I. Okay, so the first, you can see, first of all I have C6H5OH and C6H5CH2I, that is option number C here. Okay, next question, in the following compounds, okay, in the following compounds we have to find the acidity order. Okay, just predict their acidity order. Now remember, acidity order, if you have an electron withdrawing group, then acidity order increases. If it is an electron donating group, then electron withdrawing group is there, then acidity will increase. Okay, and if we have electron donating group, then acidity will decrease. Okay, these are the 2 things. Now let's, and one more important thing is, if you have like plus R effect, means donation can happen through plus R and plus I, right? So if plus R or minus R, both are more dominant than plus I or minus I. Okay, so now let us level each of this compound with what groups they are, like whether it is R or I, okay, like whether it is plus or minus, and if it is donating group, then how it is donating, through inductive or through resonance. Okay, so in this first compound there is no group present, so it is neutral. In the second compound, you can see this CH3 group, it is an electron donating group, and how does it donate? By plus I effect. Okay, now here NO2 group is there, it is electron withdrawing group. Okay, now let me tell you one more important point here regarding donation and this one. If the group is present at ortho and para position, then only it can do by resonance, but if it is present in meta position, then it will do by inductive effect. Okay, now if you see this NO2 group, okay, yeah, NO2 group is definitely electron withdrawing group, but it is present in the meta position. So here which effect it will have? Minus I effect. Okay, now NO2 here it is present, this is also electron withdrawing group. Okay, and here NO2 group, the electron withdrawing group is due to minus R effect. Okay, now we have to find the stability. So first of all, electron withdrawing group will increase the acidity. So we have this 3 and 4 will increase the acidity. Now here it is minus I, here it is minus R. I have told you resonance is more dominant, right? So that is why this one will have the highest acidity, and I have only one option with that. Now after that it will be 3, because here it is again we have electron withdrawing group. Now electron donating group is there, so it will have least acidity. So B or 2 will be least, and OH, which is neutral, which has no group, will be in the middle. So option number D is the correct answer. Next we'll move to question number 4. In which of the following reactions phenol is not obtained? Okay, so if you do NaOH and CaO, that is decarboxylation reaction, okay, and COH group is removed and you will get a phenol here. Okay, next if you have NaOH at 623 Kelvin and 300 atm, this is also Dow's process at very high temperature and pressure, this reaction. Okay, one second, yeah, this is the wrong. See, here we need to have chlorobenzene. Okay, if you take chlorobenzene at such a high temperature and pressure, you will get phenol. Okay, not from phenol, you cannot obtain from phenol. And the next one, N2C with water. This is your from benzene diazonium chloride, this one will give you, and yes, MgBr with water will also give you. So option number C is the correct answer, not obtained, because it is already phenol is there, right? You cannot obtain phenol further from phenol. Next question, phenol is a weaker acid than acetic acid because, okay, now phenol is a weaker acid than acetic acid because. So first of all, let us see the structure of acetic acid, okay, and let us see the structure of phenol. Means we are talking about their acidic behavior, means they will donate electrons. So here we have O minus, and this is the conjugate base of acetic acid, and this is the conjugate base of phenol. Now what happens here is, see, here we will have more resonating structures. Here you will have more resonating structures, okay, but you will also have, when this electron comes here, this will move here, so you will also have negative charge on carbon atom. Means the resonating structures, we are having more resonating structures, but they are not stable, okay, they are not stable. Now comparing to now acetic, this acetate ion, here if you see, this one is there, okay, now here you will get only two resonating structures, okay, here you will get only, there is no more resonating structures, only two resonating structures are there, okay, we have only two resonating structures, but in these two resonating structures both are equivalent, okay, and the negative charge is always on the oxygen atom, which is stable, right? So that is why, because of having equivalent resonating structures, acetic acid is more acidic than phenol. Clear? So now see, phenoxide is better stabilized by resonance than acetate ion. Acetate ion is better stabilized by resonance than phenoxide ion. Phenol is less soluble in water than acetic acid. Both phenoxide ion and acetate ion are stable. No, acetate ion is better stabilized by resonance than phenoxide ion because of equivalent resonating structures and negative charge on the electronegative atom. Okay. Next, propene can be converted to 1-propanol by oxidation. Which set of reagents among the following is ideal for this conversion? Propene to propanol. Okay, so if you have propene to propanol, so this is your addition of water following anti-Markovnikov's rule, and that can be done under hydroboration oxidation reaction. That is option number B here. Next, compound A, C8H10O, is found to react with NaOI, produced by reacting Y with NaOH, okay, and yields a yellow precipitate with the characteristic smell. A and Y are respectively. Okay, so we have this compound A. Okay, I'll use a different color. We have this compound A, which is C8H10O. Okay, next thing, it is found to react with NaOI. Okay, next is and it yields a yellow precipitate with characteristic smell. So here we get a yellow precipitate with characteristic smell, right? Okay, next, A and Y respectively are. Okay, so here this NaOI was produced by reacting NaOH with Y. Okay, so we have to find here A and Y. So this we know, basically if you NaOH and if you react with I2, you will get NaOI. So Y is I2, which is there in all the options. Okay, now we have to find this part. Now see, yellow precipitate if you are getting, that means you must have this group. Either you need to have this group, okay, in your compound, or you need to have this group. Okay, this is your haloform reaction. Okay, which reaction is this one? Haloform reaction. So now we can see in which of this compound we are having these two groups. So I need to have CH3CHOH. That is not present in this one. It is having CH2OH, so eliminate this option. Here also I don't have CH3COH, so I can eliminate this option. Here I can see CH3CHOH is there, right? So this reaction, this can be the answer. Here also I don't have the CH3CHOH, so option number C is the correct answer here. Okay. Next question, compound A on treatment with Na gives you B. Okay, compound A is there and on treatment with Na it gives you compound B. Okay, and with PCl5 it gives you C. So if you further treat it with PCl5 it gives you C. Okay, and B and C react together to give you diethyl ether. B and C can react together to give you diethyl ether. Okay, next what we have, A, B, C respectively are. So first of all, when you have this sodium, you are treating it with sodium, you are getting this B, and then we are treating it with this one PCl5 to give you C. So C must be means I can say that this C, okay, this has to be a Rx, okay, and this group, okay, this group has to be a ROH. Okay, so let us find out where are we matching this one. So the C is Rx in two options. Okay, so that means I can eliminate the other two. Okay, and B is a ROH. Okay. Okay, so see, it can be ROH or a salt of this one also, right? So when you are treating it with sodium, you will get RO minus Na plus, right? So this one has to be an ROH, this one has to be RO minus Na plus, right? So here if I get, you can see this is C2H5OH, this is C2H5O minus Na plus, and then when these two will react, you will get here the diethyl ether, right? So option number D matches all the condition. So option D is the correct answer. Next, the structure of the intermediate A in the following reaction is. Okay, so this is your preparation of phenol by cumene method. Okay, so here what happens, the first structure we get is this peroxo compound. Okay, and after that, so you just need to find A. So that is your this one. Sorry, here there is a small error. You can see that this side there is not a CH3. Okay, this is the group CH3 COOH, which is option number C here. Next, the product of the following reaction is, so this is your anti-Markovnikov's addition of water, so you will get propane 1OL, which is your option number B here. Okay, this all other options are incorrect. Next we'll see question. Now we'll go to the 2-marker question section. Okay, 2-marker questions are very important because they are easy and mostly very easy simple reaction based or name reactions questions. Okay, so let us see the next question here. Write the product for the following. So here you have taken propene with H plus and H2O. So this will give you Markovnikov's addition of water, and here you will have the product CH3, CH, OH and CH3, which is propane 2OL. Okay, which is propane 2OL. And then if you have B2H6, H2O2, OH minus, so that will give me CH3, CH2, CH2OH. Okay, anti-Markovnikov's rule. So that is propane 1OL. Clear? Next question, what is the effect of electron donating substituents on acidity of alcohols? And next question, alcohols are weaker acid than water, give reason. Okay, so this is one question, this is one question, 2 question, 2 marks. So electron donating group will decrease the acidity, that's the first part. Alcohols are weaker acid than water. Now see, if you consider alcohols, you will get RO minus, and if you consider water, it is HO minus. Now R is having what? Plus I effect, it will increase the electron density, and this conjugate base is unstable. Okay, so that is why alcohols are less acidic than your water. So how can I write this answer? So first thing, electron donating group will decrease the acidity. Next thing, alcohols are weaker acid because the alkoxide ion, means RO minus, is destabilized due to the electron donating nature of the R group. Okay, next let's see the question number 3 here. What is esterification reaction? Give an example. Or what happens when ethanoic acid reacts with methanol in presence of concentrated H2SO4? Give the equation and what is the name of the equation. So what is esterification reaction here? Yeah. So what is esterification reaction? The reaction between acids and alcohols to form esters, okay, in presence of concentrated sulfuric acid is called as esterification reaction. Now give an example. I'll use the same example so that both the answers can be covered here, okay. So you can see you have to react ethanoic acid with methanol, okay. So if I have ethanoic acid, okay, and I have methanol, okay, that will give me ethanoic acid plus methanol in concentrated H2SO4. So here what will happen, from acids this OH group, and from alcohol this H group will be removed, so there is minus water molecule is formed, okay, and then you have CH3 C double bond O CH3. This is the ester formed, okay. So equation we have given, this example is also given. What is the name of the reaction? That is your esterification reaction, okay. Next, what is Lucas reagent and how would you distinguish between primary, secondary and tertiary alcohols by Lucas reagent? So Lucas reagent is a mixture of anhydrous, okay, what is it? Anhydrous ZnCl2 and concentrated H2SO4, sorry, concentrated HCl, okay, is called as Lucas reagent. And how it is used to differentiate between primary, secondary and tertiary alcohols? So here you have to understand that tertiary alcohols, okay, reacts immediately with Lucas reagent, reacts immediately, I wrote wrong spelling, just a minute, yeah, reacts immediately, okay, tertiary alcohol reacts immediately and gives you turbidity, okay. Now secondary alcohol reacts after 5 minutes, okay, and primary alcohol does not react at all. Clear? So these are the 5, this is how you can differentiate using Lucas reagent. Next, what happens when vapors of primary, secondary and tertiary alcohols are passed over heated copper at 573 Kelvin? So you know what happens here. Here we have dehydration reactions, okay, we have dehydration reaction. So primary alcohols, okay, will give you aldehydes. Now example, suppose I have CH3 CH2 OH, so with copper at 573 Kelvin we will get CH3CHO, okay. Next, secondary alcohols will give you ketones, okay, and that will be equal to CH3 CHOH CH3, and if you treat it with copper at 573 Kelvin, that will give me CH3 CO and CH3, okay. Next, third one is, if I have tertiary alcohol and you treat it with this one, then we will get alkenes, okay. Now here example, we have CH3 CH, I'm just writing like this, then you have OH and CH3, and if I use copper at 573 Kelvin, then there will be dehydration, this H and OH will be removed and I will get CH3C double bond CH2 CH3, okay. So this is how the reaction takes place. Next question, describe the manufacture of ethanol from fermentation of sugar. Yeah, this is important question because from here MCQ can also be asked. So what happens here is, see, first the reaction you have to understand that the sugar, from sugar how the fermentation takes place. So the sugar in molasses, okay, not every sugar, the sugar in molasses or sugar cane or fruits such as grapes is converted to glucose and fructose in the presence of an enzyme, okay. And what is the name of this enzyme? It is invertase. Now glucose and fructose undergo fermentation, okay, in the presence of another enzyme called as zymase, which is found in yeast. So please understand, first sugar is converted to glucose by using the enzyme invertase, okay. Then the glucose and fructose that is produced are further converted to ethanol by the enzyme called as zymase, and this zymase is found in yeast, okay. So there are two steps, so we'll see that in the reaction here. So first, this is the sugar, okay, this is sugar. This sugar can be from molasses or from grapes or from sugar cane, anywhere. Using this enzyme invertase, it is converted to glucose and fructose. Next, this glucose or fructose is converted using zymase to ethanol, okay. Next, we'll see question number 7. How would you prepare phenol from benzene via sulfonation? How would you prepare phenol from diazonium salt? And how would you prepare phenol from cumene? Now, let me tell you this this is most important question. So, any of this can be asked, but the probability of this one is much higher, okay. So, I'll show you all the 3 reactions. So, benzene is treated with oleum to give you benzene sulfonic acid, and then on heating with NaOH, we get phenol. This is the first part. Okay. Now, how will you get from diazonium salts? So, diazonium salts are hydrolyzed to phenols by warming with water. Okay. Here we have simple reaction. You take aniline, then you take benzene diazonium salt, and you just treat it with nitrous acid, that is NaNO2 and HCl. You will get benzene diazonium chloride, and then you have warm water that will give you phenol. Okay. Next, we have the cumene one. How do you prepare phenol from cumene? So, cumene is oxidized in presence of air to give you cumene hydroperoxide. It is converted to phenol and acetone by treating it with dilute acid. Okay. So, here you have cumene, and then you have cumene peroxide, and then when you H plus in water, if you treat, you will get OH plus CH3COCH3. Okay. Next, we'll see question number 8. Electrophilic substitution reactions of phenols occurs at ortho and para position respectively. Give reason. So, if you draw the resonating structures of this phenol, you can see that the electron density increases at ortho and para position only. So, that is why the incoming electrophile is directed to ortho and para position. So, that we will see from the resonating structure. See, phenol has a OH group which increases the electron density in the benzene ring by donating the lone pairs of electron on the oxygen atom. Now, you need to draw this resonating structure to show that the electron density actually increases at ortho and para position only. So, first step, the lone pair here are coming in conjugation. This bond is shifting here. So, you can see the electron density has increased at ortho position. Now, after that, this one will come here and this one will come here. You can see that electron density has increased at para position. Now, again, this one goes here, this one comes here. You can see the electron density has increased at ortho position. So, because this electron density increases at ortho and para position, the incoming electrophile will be directed to these positions only. Okay. Next, question number 9. Among ortho and para nitrophenol, which one has higher boiling point and higher vapor pressure? Now, see the structure of this ortho nitrophenol and para nitrophenol. So, I'll draw here first ortho nitrophenol. Okay. In orthonitrophenol, what we have is intramolecular hydrogen bonding. Now, if you see para-nitrophenol, okay, you have para-nitrophenol, oh, sorry, one second. So, if you see para-nitrophenol, okay, what did you observe here? In para-nitrophenol, there is intermolecular hydrogen bonding, and in orthonitrophenol, it is intramolecular hydrogen bonding. Now if there is intermolecular hydrogen bonding, the molecules will be closely packed and it will be very difficult to boil them. So higher boiling point will be in case of para-nitrophenol. The reason here, what you will write, the reason is due to intermolecular hydrogen bonding, right? Intermolecular hydrogen bonding. Okay, next what we have, higher vapor pressure. Higher vapor pressure means it can easily evaporate. Now when can it easily evaporate? It can easily evaporate if the molecular attraction is weaker. So if there is intramolecular hydrogen bonding, so it can easily evaporate because it is not bound to other molecule, right? It can itself go and evaporate. So that is why this one will have higher vapor pressure due to intermolecular hydrogen bonding. Clear? Next question. Yes, explain Coles reaction, or how do you convert phenol to salicylic acid by Coles reaction. So in Coles reaction, what we have sodium phenoxide ion that reacts with the CO2 followed by acidification to give you salicylic acid. You can see first we have this phenoxide ion, it reacts with carbon dioxide and H plus to give you this particular compound which is salicylic acid. Okay. Next, what is Reimer-Tiemann reaction, and explain. So same like it is also for the preparation of salicylic aldehyde. So here we have phenol on heating with chloroform in the presence of sodium hydroxide at 340 Kelvin followed by hydrolysis gives orthohydroxybenzaldehyde. Okay, this reaction is known as Reimer-Tiemann reaction. So first we have phenol here, then you take this particular reagent, that is CHCl3 plus aqueous NaOH, and then we get this particular compound, and then you treat it with NaOH. Here both the chlorine are replaced with OH and OH. After that there is dehydration, there is CHO, and we will get this particular compound, that is salicylic aldehyde. Next one, explain Williamson ether synthesis with an example. So here what we have, in Williamson ether synthesis you have Rx. Okay, so I'll just draw here. So you have in Williamson ether synthesis Rx plus R dash ONA. Okay, now here what will happen, this R dash O minus Na will react with R. Okay, you will get R dash OR. Okay, and here you have to remember something, that is this Rx must be a primary halide. Okay, it must be a primary halide. Alkyl halides on heating with alkoxide in alcoholic medium gives ethers, and this reaction is called as Williamson ether synthesis. You can take one example, that you have CH3Cl plus CH3CH2O minus Na plus. Okay, so this one will give here this one, and this bond will break. So you will get here CH3CH2O CH3 plus NaCl. Okay. Next we'll see question number 13. Which of the following is a better method for the preparation of tert-butyl ether? Tert-butyl ethyl ether. Now I told you, whenever you prepare anything this type of ether through Williamson ether synthesis, the Rx must be a primary group. Okay, now here you see this Rx is what? It is a tertiary one, but here if you see, this is the primary one. So that is why which method will be preferred? Second method will be preferred. The reason being, here the Rx is a primary halide. Rx is primary halide. Okay. Next, see the question number 14. What happens when diethyl ether is heated with limited amount of HI and excess amount of HI? Okay, so this is a good question. So first of all, diethyl ether is there. I'll do the first one. Okay, so diethyl ether means CH3, CH2O, CH2, CH3. Okay, you can see both the side, that is same group. So you will have one side CH3, CH2OH, and in other side you will have CH3, CH2I. Okay, now what will happen when you heat it with further, if you give further excess of HI, okay, what will happen is this one gets protonated. So CH3, CH2OH is there, that when you treat it with HI, it gets protonated CH3, CH2O plus H2. Okay, and then I'll erase this one. Okay, now this I minus can attack here. Okay, this I minus can attack here, this one will go, so I will have CH3 CH2I. So 2 molecules of this one will form. The first one will form, and with excess of HI, this alcohol will also get converted to this one. Okay. Next, we'll have complete the following equation and mention whether the reaction is SN1 or SN2. So I've completely explained you the cleavage of HI. So you have seen one side there is tertiary, one side there is primary. If one side tertiary, one side primary, then first of all, which mechanism will be followed? SN1 mechanism will be followed. Next, the I minus will attack on the nucleophile. So I will get the product here, CH3 whole 3 Ci plus this one is CH3OH. Okay. Next, we'll see now long answer questions, okay, 5 marker questions. So there are 3 important mechanisms in this particular chapter. So all the 3 mechanisms you should prepare thoroughly, okay. The first question is explain the mechanism of dehydration of ethanol to ethene. This dehydration, all the mechanisms in this chapter can be a 3 marker question, okay. So dehydration of ethanol to ethene. So how this dehydration takes place? See, first of all, I'll explain the steps. So what you have, first thing is there is protonation of this alcohol. Okay, this is the first step. So you get what? CH2O plus H2. Now why is this protonation? To make water a very good living agent, okay, living group. Now OH, removing OH is difficult, but removing O plus H2 is easy. So that is why we create this. Now after that there will be what? You have this one, CH2 O plus H2. So here this O plus H2 will leave and you will get CH3 CH2 plus. Now after that, if you see, we have like this. Okay, now this bond will shift here and you will get this particular compound. Okay, so this is your dehydration of ethanol to ethene. Okay, these are the 3 steps. First step is protonation of alcohol, second step is formation of carbocation, and third step is this alkene formation. Okay, so next one I will explain, I'll tell you how to write in the next slide, but let us complete these 2 questions first. Identify A and B in the given reaction. So this is what? This is your Kolb's reaction, right? So what will be A in this reaction? Salicylic acid. So A formed here is, we have just discussed this reaction in the previous some slides. So this one will be, okay. Next, CH3 whole 3 COC2H5. So here if you remember, this one side is tertiary group. So I will attack here. So B will be CH3 whole 3 Ci. Okay. Now I'll show you the mechanism how to write. The first step is protonated alcohol. Okay. The second step is formation of carbocation. This group moves here and there's a carbocation here. After that there is elimination or deprotonation, you can think, where you will get the ethene molecule. Okay. Now let's go to the second question. Identify A, B and C in the following reaction. So when phenol is treated with bromine, okay, so it it takes intense bromination happens and all the ortho, para and positions are actually brominated to give you OH. Then we have Br, Br and Br. Okay. Next, with phenol with zinc, you will get what? You will get here zinc dust. Phenol with zinc will give you benzene. Your B is benzene. Okay. Next question is C2H5OH plus Na. Okay. So here if you see, alcohols is reacting with the metal. Okay. So when alcohols will react with metal, what will be the product? You will have this alkoxide ion and C will be hydrogen gas is released. Okay. So what will be C here? C will be hydrogen gas. Okay. Next question, how do you prepare phenol from aniline? So this reaction also we have discussed. So first of all, what you have to take? You have to take phenol here. Okay. Then prepare from aniline, right? Okay. So first you have to take NH2. Okay. Then you need to treat it with HNO2, nitrous acid. So that will diazotization takes place here and you will get N2 plus and Cl minus. Then if you treat it with warm water, okay, in that case this one will become OH. Okay, now how do we write this reaction? How can you write this reaction? So you have to write aniline. Okay, aniline is treated with nitrous acid to form benzene diazonium chloride. Okay, to form benzene diazonium chloride. Okay, and okay, which further reacts with what? Warm water to give phenol. Clear? So this is the answer for the second part. Next question, explain the mechanism of dehydration of alcohols into ethers. Now see, dehydration of alcohols can give you alkenes also and can give you ethers also. So mechanism for that we have to write, and how anisole reacts with acetyl chloride, that we will see. So first let us see the first part, that is the mechanism of dehydration. So here the first step remains same, that is the protonation of alcohols. Okay, so here actually there is protonation. Okay, so protonation of alcohol takes place. I'll just use a red color, it is more easily visible. Okay, now after this protonation what happens, there is another alcohol is there, another alcohol molecule. Now see, after this protonation, this carbocation, this carbon is positively charged, because oxygen is positively charged, it will pull electron towards itself. Now this is electrophilic. Now another alcohol molecule lone pair will attack on this one. Okay, and this water molecule will go out. So what we will get? CH3 CH2 O plus H CH2 CH3. Now this compound is there here, O plus H. Here there will be deprotonation. Now this H goes and we will get this particular compound, that is diethyl ether. Okay, next, how anisole reacts with acetyl chloride. So that reaction I'll write here. So anisole is OCH3. Okay, how anisole reacts with acetyl chloride, that is CH3COCl. Okay, now this one is electron donating group, so again it will be ortho para substitution. So you will get two product here. One is where OH is attached to this ortho position COCH3, and there is another product where the OH is attached to the para position. Okay, this is done. Okay, next we'll see question number 4. Explain the mechanism of hydration of alkenes to alcohol. So I told you there are 3 mechanisms, right? So this is the third mechanism. The first mechanism and third mechanism students get confused. See, there is one mechanism for alcohols to alkenes. Okay, that is your dehydration. The another one is alkenes to alcohols, which is your addition reaction. Okay, so that question is asked here. So next is complete the following reaction. Okay, so let us first do this one, then in the next slide we will go to the mechanism part. So H2 and H plus is nothing. What it will do? It will add water following Markovnikov's addition. So what will be B here? CH3 CHOH CH3. Now with CrO3, what it is a very good oxidizing agent. Secondary alcohols are converted to ketones. Clear? We'll get this, right? So I can see the mechanism for the addition of alcohols or addition of water to alkene. So first of all you have to have this alkene, and then this water gets first protonated. Okay, the water gets protonated to give you H3O plus. Now this alkene attacks on this one H, and this water molecule is released and we get a carbocation here. Now in the second step what happens? The water molecule reattacks on this carbocation to form this protonated water. Okay, and after that there is deprotonation here to give you alkene. So this mechanism, please be very careful, do not interchange. This is from alkenes to alcohol and the first one was from alcohols to alkenes. Okay, majority of the students do mistake here, so please prepare this mechanisms properly and read the question properly when it is given in the exam. Okay, Next, we'll discuss the important topics that you must remember. So, name reactions. First is Williamson-Coles reaction, Riemer-Tiemann, Fidelkraft, and esterification. Okay, these are some important name reactions that you should remember. Mechanisms. There are 3 mechanisms in this chapter: alcohols to alkenes, alcohols to ethers, and alkenes to alcohols. Okay, majority of the time this is asked and this is asked. Okay, so don't get confused in between these two. Read the question properly and then answer. Okay, so students, thank you so much, and in this video I have covered all the important questions, mechanisms, name reactions, fill in the blanks type questions. So yes, do practice these questions, and if you're done with this, then only go for more questions. Okay, first complete these many questions. Thank you so much. All the best for your final exams.